this lunch seminar. Aleena is a second-year PhD at University of Oxford, where she's working with Leslie Gray and Scott Osprey. Before she started at Oxford, though, she's originally from India and got her bachelor's and master's at IISER Pune. And in her master's work, she was focused on equatorial Kelvin waves, but now at Oxford, she's looking at the stratospheric semi-annual oscillation and model biases with that oscillation. So I met Aleena at a conference back in October focused on the stratosphere, tropospheric processes and their role in climate. And I'm excited to hear her present her work to us at GISS, and hopefully we can gain some insight on modeling the semi-annual oscillation and its relevance. So with that, I will let Aleena start whenever she's ready.
Yeah. Hi everyone. Thank you, Molly, for introducing me, and thank you, Maggie, for arranging it all. So I'll start. Okay. So this right here is the one-line summary of the project I have been doing in the past year. So on alleviating semi-annual oscillation or SAO wind biases in the climate models. So what I will be explaining today is okay. So first I will explain the model SAO biases that we see, and then I will try to compare the model SAO with the reanalysis SAO and also different forcing terms that give rise to SAO, and try to identify the causes for the SAO biases that we see. And finally, I will look into some preliminary experiments that I have done to see if we can improve the SAO representation in the climate models. So first, okay, that right there is me at the beginning of the project wondering what is semi-annual oscillation and all those things. So to put things in perspective, here we have the troposphere, and as you can see, Hadley cell, polar cell, and jet streams, all those events happening in the troposphere. And just above that is our stratosphere. And if we focus on the equatorial region, we have the quasi-biennial oscillation, and I'm sure everyone is familiar with that. And right above that is the semi-annual oscillation, which is what I am looking at. So semi-annual oscillation is very similar to QBO in the aspect that it is alternating westerlies and easterly winds happening at the equator, but it has a 6-month periodicity. So now we have all other events happening here, like the polar vortex, planetary wave breaking, and Brewer-Dobson circulation, etc. And we will come back to that. But first, we will look at semi-annual oscillation from some satellite observation data and see how it is in the atmosphere. Okay, so here is a plot from Smith et al. 2017, and she has basically plotted the zonal mean, zonal wind climatology, time versus height plot, and she has basically showed the semi-annual oscillation from SABRE and MLS observation data here. So as you can see, if we focus on this 1 hectopascal region, you can see there is the easterlies and westerlies alternatively occurring at the region, and this is basically with a 6-month periodicity. So that is why it's called the semi-annual oscillation. And one thing to notice here is that if we look at this first half of the year, which is basically the northern hemisphere winter months, we can see it has a much more magnitude than the second half of the year. So this suggests that there is an annual cycle within the semi-annual oscillation. So that is another property that we are interested in. And also both westerlies and easterly winds go up to 30 meters per second or higher in magnitude. And if we look at the westerly winds, we can see that it kind of propagates downwards, which suggests that it may have a forcing mechanism similar to QBO, like the wave dynamics. And the next is the easterly phase. And as you can see, it kind of appear at a range of altitudes together. So it makes more sense for it to have a forcing that is applied horizontally, not vertically. So yeah, these are basically the important properties of semi-annual oscillation that I'm interested in. And we will now move on to understand different forcing mechanisms that give rise to the semi-annual oscillation. So here is again the plot that we saw earlier. And as you can know already from what the different forcing mechanisms in the stratosphere, there will be waves that propagate upwards, and those that are not filtered by the QBO will be able to propagate further upward and help to generate the semi-annual oscillation. And also there are waves from the higher latitudes which can laterally propagate into equator, like the planetary waves here. And then there is the Brewer-Dobson circulation that is happening here. So this can basically advect winds from one hemisphere to the other. So basically these are the different forcing mechanisms that give rise to the semi-annual oscillation. But I will individually look each of the phase of the SAO and see how it happens. So here, first we will focus on the easterly phase of the semi-annual oscillation. And as you can see, there is the Brewer-Dobson circulation happening here, which can advect the winds from the summer hemisphere to the winter hemisphere. If we look at a composite plot of the U wind in the DGF time, you can see that in the summer hemisphere, it is mostly easterly winds that is happening, and the winter hemisphere mostly have the westerly winds. And what happens is that when the Brewer-Dobson circulation occurs, it kind of advects the easterly winds in the summer hemisphere through the equator to the winter hemisphere, and this kind of gives the easterly forcing for the easterly phase of SAO. And this makes much more sense because it is appearing in latitude, so it kind of appears at all altitudes together, which will give the semi-annual oscillation easterly phase a constant velocity at all altitudes coming at the same time. Now, it can also have the wave forcings which are coming from the QBO region and higher latitudes, but the main forcing mechanism that gives rise to the easterly phase of the semi-annual oscillation is this meridional advection from the Brewer-Dobson circulation. And the next one is the westerly phase. And in the westerly phase, it mainly occurs in the spring and autumn times. And so the Brewer-Dobson circulation will be weaker in this time. So the advection from Brewer-Dobson circulation can be there, but it will be much weaker. So the wave dynamics then plays a major role here. And so the waves that are not filtered by the QBO can propagate upward and give rise to the westerly phase of the semi-annual oscillation. So these are the different forcing terms that give rise to the SAO. Now I will move forward and explain why am I studying the SAO. Like SAO is so high at altitude and we'll be wondering why it is important. So right here is a paper by Leslie published last year, and she has shown that actually the westerly to easterly phase transition time of SAO is kind of important in predicting the time of the sudden stratospheric warmings. And as you all know, that like sudden stratospheric warming prediction is important because it can affect the surface weather. And so if we get this transition timing of the westerly to easterly of SAO get correct, then only we can accurately predict the timing of the sudden stratospheric warmings. So that's why I am interested in this. And but the issue here is that in this paper by Anne Smith, she has shown that most of the climate models has an easterly bias, which kind of makes our life difficult because if the models have an easterly bias, it kind of affects the transition timing and it can further affect the sudden stratospheric warming timings and all those things going on there. So what I basically tried to do is I will try to see why this easterly bias in the climate models are present there and try to understand how we can like at least reduce the biases in the climate model so we can get a better representation of SAO in the models. Okay. Now, in order to understand the climate model biases, I will need something to compare it with. And so I have looked at some reanalysis here. I can't actually use observations because it is difficult to calculate some of the terms I want for my comparisons from observation. So that's why I have focused on the reanalysis. And here I have three of them, ERA-5, ERA-interim and MERRA2. And first, if we look at this third panel, ERA-5, above 1 hectopascal, you can see that the westerly winds is going crazy. It has magnitude 70 meter per second or higher definitely, and in some cases it reaches up to 150 meter per second. So it is actually not realistic compared to the observations that we have seen earlier. So we will have to keep aside ERA-5 for now, but maybe we can revisit it and see what is going on there later on. But then we have ERA-interim and MERRA2, and both of them actually reproduce semi-annual oscillation pretty well. It has the 6-month periodicity and reasonable magnitudes as we want to see. But in case of ERA-interim, the one thing is that its model top is 0.1 hectopascal, which is a bit lower than what we have at MERRA2. But the other thing is MERRA2 kind of has longer westerly wind regimes compared to ERA-interim. And this is actually true when we look at the observations too. The westerly wind regimes are kind of longer in observations. So also, MERRA2 assimilates MLS observational data from 2004 onwards at these heights. So it is better to stick with the MERRA2 for now as our truth. And we will move forward with reanalysis MERRA2 and compare it with the model data. Okay. Now to see.
Okay, Aleena, are you okay if we ask questions?
Yes, sure. Go ahead.
Yes. So why is MERRA2 doing a better job? I mean, are they ingesting data that's not available to ERA products?
Yeah. So in the case of MERRA2, one thing is it assimilates the observational data at these heights, which obviously makes it better. And the other thing is that in ERA-interim, it doesn't have a non-orographic gravity wave parameterization, but MERRA2 has that. And also it is kind of tuned to get the QBO and SAO correct. So that's why MERRA2 is kind of doing a better job here.
Thank you.
Okay. Now we will compare the model and reanalysis. So here I have used vacuum, but all in this Smith et al. Paper, she has shown that all the models have this easterly bias, and I just have Hadgem also here just to have for a comparison. So first, anyway, I'll focus on the biases. So as you can see, the MERRA2 winds are here, and if we focus on this westerly regime, we can see that in the MERRA2, it goes up to 40 meter per second, definitely the westerly phase. But in vacuum, we can see it barely reaches 20 meter per second. So there is definitely an issue in the westerly phase magnitude going on. And then if we look at the phase transitioning timing, in MERRA2, most of the easterly winds comes in December, like from 0.6 hectopascal to 5 hectopascal transition happens at this month. But if we look at vacuum, by the time it's October, the transition from westerly to easterly happens, it reaches till 1 hectopascal, so which is kind of a bit early. And so we have this early westerly to easterly transition going on in vacuum. And the other thing is the annual cycle. So as I have mentioned earlier, the northern hemispheric wind magnitudes are a bit higher than the summer winds, and MERRA2 has that, and vacuum also has that, but it is not as strong as MERRA2. In MERRA2, easterly phase almost disappears in the summer, which we can't see here. So we kind of have a weaker annual cycle too, which is actually pretty clear from this plot here, which is a fast Fourier transform in time of the U wind. And we have the semi-annual variability here, annual variability here, and QBO variability here for MERRA2 and vacuum. So in vacuum, almost all the variabilities are lesser in magnitude, but yeah, as you can see, we can see the weaker annual cycle component from here as well. So I have yeah. And also, if we focus on Hadgem 2, this last panel is Hadgem minus MERRA2, and you can see throughout the year it has negative values, which kind of suggests it has an easterly bias. So basically, we have established different model biases that we see, which is weaker westerly winds and early westerly to easterly phase transition and weaker annual cycle. Okay. So I have explained the model biases now. Now I will be comparing the model and reanalysis SAO forcing terms and try to see where these biases originates from. Okay. So for that we have the transformed Eulerian mean momentum equation, which makes my job a lot easier. So all the forcing terms that we have seen earlier is here in the mathematical form so that I can just plot it. And on the left hand side, I have the du by dt, which is basically the tendency in zonal wind. And on the right hand side, I have different forcing terms that give rise to this change in the zonal wind. So the first one is the meridional advection. So if you remember from earlier plot, it comes from the Brewer-Dobson circulation. So that term is the one here, and then the vertical advection. It partially comes from Brewer-Dobson circulation, but it can also have effects from the induced circulation, which is due to wave dynamics. So basically, if there is an easterly wave forcing, it kind of creates an upwelling, and the westerly wave forcing will create a downwelling. So that induced circulation will also affect the vertical advection here. And the third term is the EP flux divergence, which will represent the resolved wave forcing. And the last one is for the subgrid scale process. So I'll later show that it is almost completely due to the gravity wave drag. Okay, now here is basically a summary plot of all these forcing terms. So the blue line here is the meridional advection, and as you can see, it is mostly giving the easterly forcing, which we have already seen earlier. And then we have resolved wave forcing, which also seems to be in average give an easterly forcing, and the vertical advection and gravity wave forcing seems to be moving towards the westerly forcing part. Now we will individually look at all of these forcing terms and try to see what are the differences between the reanalysis and model. So first I'll be focusing on advection, so the meridional and vertical advection. And this here is the meridional advection plot. So the color contours here are the meridional advection, or this term on the right hand side. And I have basically separated into 6-month windows, which I have done earlier also. I forgot to explain it. So it just, I wanted to show the annual cycle here. So the winter hemisphere and the northern hemisphere winter and northern hemisphere summer differences. So yeah, and I have the MERRA2 vacuum and MERRA2 minus vacuum shown here. And if we look at the terms in MERRA2, we can see that during the JJA and DJF months, which is basically the northern hemispheric winter and southern hemispheric winter months, we have the Brewer-Dobson circulation happening, and exactly at that time we can see this easterly forcing coming in during the both times, and this kind of exactly matches the easterly phase of the semi-annual oscillation. So we can know that the meridional advection is being an important part in forcing the easterly phase of SAO. Now, if we look at vacuum, it is definitely there. At least in summer month, the magnitudes are also kind of similar, but in winter months, you can see that there is a reduction in magnitude, but the timing is correct. But the thing here is that already the westerly phase in vacuum is weak. So even with this forcing, vacuum is able to produce a decent easterly phase. But if we get the westerly phase magnitudes correct, this forcing might have to increase so that we will need extra forcing to get the easterly phase also correct. So yeah, basically we have meridional advection, which gives one of the major easterly forcing, and it appears on the northern hemisphere and southern hemisphere winter months. And in vacuum the timing is correct, but the magnitude is not strong enough. Now we will move on to the vertical advection. So it is much similar to earlier plot, and instead the color contours here are the vertical advection. And if we look at the MERRA2 panel, we can see that on the second half of the westerly phase, there is strong positive forcing coming in due to the vertical advection. This suggests that in order to maintain the westerly phase of SAO, a positive vertical advection is kind of important in MERRA2. But if we move on to vacuum, we can see that that forcing is completely absent. So this is a huge difference between MERRA2 and vacuum. But the thing here is that this vertical advection is actually affected by the wave dynamics. So we will have to first understand how the resolved or gravity waves are behaving in these regions to identify if the vertical advection is actually different in these two cases. So in summary, in MERRA2, vertical advection is really important to maintain the westerly phase, but vacuum doesn't seem to have this forcing at all. But it depends on the wave forcing, so we will look at that. So we will now move on to the wave forcing, which is the resolved wave forcing and gravity wave forcing. So the last two terms in our equation. The resolved wave forcing. So the colored contours are now scaled EP flux divergence, which is the term here. And in MERRA2, if we see that right before the westerly phase, there is this westerly is EP flux divergence happening, and this suggests that resolved waves kind of plays in a role of transitioning from easterly to westerly phase in MERRA2. But if we look at vacuum, we can see that that forcing is completely absent. So model doesn't have as much resolved waves as MERRA2, and we will need to improve that in the case of model. And I have kind of looked at different wave components, but this is just a preliminary analysis. But so here what I have is a wave number, frequency, power spectra on x-axis wave numbers and y-axis frequency, and the different dispersion curves here corresponds to different waves. So we have Kelvin wave here, inertial gravity waves here, and Rossby waves here. And this here is at 100 HPA, so it is down below QBO, and we can see the magnitude of Kelvin waves here, and which basically gives the westerly forcing. And if we move to 10 hectopascal, which is after the filtering by the QBO, so what we will expect is most of the low speed Kelvin waves will be absorbed by the QBO, and those reaching at higher levels will be the high speed Kelvin waves that are remaining. And as you can see, there is a shift in the phase speed of Kelvin waves, and it is clear that the higher speed Kelvin waves are reaching at higher altitudes. Now, if we compare the MERRA2 and vacuum in this case, we can see at MERRA2 in the low wave number region, it has higher magnitudes compared to vacuum, which suggests that in the resolved waves, the Kelvin waves are actually weaker in vacuum. But there can be other waves also, which like the gravity waves, which gives rise to the westerly phase of SAO. So we will move forward and look into the gravity waves now. So in order to look at gravity waves, we can have two approaches. One is that in our equation, the only term now remaining is x bar. So if we subtract all the other terms, the meridional advection, vertical advection, and resolved wave forcing from du by dt, this will give us the residual term, which is the x bar. And in this right hand side plot here, I'll show that it is mostly from gravity wave drag. So this left four plots here is purely the gravity wave drag, and the right plots are residual minus gravity wave drag. So you can see that most of these terms are close to zero, which suggests that residual is mostly composed of gravity wave drag. And so I'll focus on the residual term now. So the color contours here in this plot are the residual term. And if we focus on the MERRA2, in the westerly phase region, just at the beginning of westerly phase, we can see there is a huge westerly forcing happening due to the gravity wave drag. And this kind of suggests that it is a really important forcing in establishing the westerly phase of the semi-annual oscillation. But if we look at vacuum, and so for example, if we see at the difference plot, we can see that there is an positive forcing in vacuum, which is basically because the vacuum gravity wave drag kind of happens a bit earlier than MERRA2. So there is a timing difference here. And if then the magnitude of vacuum gravity wave drag is actually lesser than MERRA2, which gives rise to this negative values here. So this suggests that in model, the gravity wave drag kind of happens a bit earlier, and its magnitude is not as strong enough as the one in MERRA2. Now, another thing is the easterly gravity wave drag here. If we compare MERRA and vacuum, we can see that vacuum doesn't almost have an easterly wave forcing there, but MERRA2 has strong easterly gravity wave drag going on. And this actually connects with the vertical advection that we saw earlier. So this easterly gravity wave drag here will give rise to an induced upwelling, which results in the vertical advection positive values that we saw earlier. So what happens is MERRA2 is the negative values from the gravity wave drag kind of balances the positive values from the vertical advection, and it kind of goes to zero. And in case of vacuum, both of these forcings are absent. So overall, it gives the same result, but there is a difference in how it is applied. But so in summary, we can see that both the resolved waves and gravity wave drag in the model kind of needs to be improved to get the SAO a bit better, at least the SAO westerly phase. So that's what I have here so far. we have seen that the easterly bias is likely due to the underrepresentation of both result and parameterized gravity waves. So the next step for me is to conduct different experiments and see if any of this can help to improve the SAO representation. So I will be exploring possible gravity wave drag modifications and see if that will help. And the next is vertical or horizontal resolution and see if that will help to resolve more waves. And third is nudging the lower level winds so that it will help to correct the wave filtering and more accurate waves will be reaching the semi-annual oscillation region and see how that helps. So yeah, so far I have explained the model biases and now I have compared the reanalysis and model and kind of come up with two causes that can cause the SAO bias in the model. And now we will look onto the experiments. So for experiments, I have used unified model. And so if you remember, I have already shown that unified model also have the same bias as we saw in vacuum. And so I will be like doing these three experiments in unified model and see if any of these will help to improve the semi-annual oscillation in the model. So I will be focusing on the gravity wave parameterization, resolution, and QBO nudging, which is basically the lower level winds relaxation. The first is gravity wave parameterization and resolution. What I have here is westerly and easterly winds magnitude average. On the top, I have the positive winds, which is westerly wind magnitude, and it is averaged at the 0.3 hectopascal. And on the lower half is the easterly wind magnitudes, which is averaged at 1 hectopascal. So, and the right hand side, the plot on the most left is from MERRA2, so which we will consider as our truth for now. So first we will focus on the gravity wave parameterization experiments, which is on this right hand side. And this is basically, I have tried changing the Wavell star or the magnitude of the spectrum that is dispersed, etc. But as you can see, most of the westerly winds are still in the lower half of the magnitude, and the easterly winds are also not improving. It is still showing high magnitudes compared to the MERRA2 here. So this suggests that the gravity wave parameterization experiments, at least the ones I have done, is not like helping to improve the SAO. I will be focusing on much more experiments based on gravity wave drag in the future, but none of these seems to help the SAO. Now, the vertical resolution experiments. So if we move from right to left, is this is in the increased vertical resolution direction. So the plot here is from 85 level model, and this one is 88 levels, and we have 173 levels into configuration here, and 242 levels into configuration here. And if we move from left to right, so we can see that there is an improve in the westerly wind magnitude, but it is not that much, but still there is an improvement. And the easterly wind magnitudes kind of stays the same, but once it reaches L242, it kind of decreases and come close to MERRA2. So this suggests that improving the vertical resolution has an impact on the SAO with magnitudes, but we will see if it is actually enough to improve the increased Hall resolution to 242 levels. So here I have the zonal mean zonal wind magnitude climatology, and this one here is from 85 level model and this is from 242 level model. And as you can see, the westerly phase magnitudes kind of improve when we come to the 242 level model. Not that much, definitely not what we want to see, but there is an improvement. And the easterly phase, the second half actually reduces in magnitude, which kind of helps in the annual cycle that we mentioned earlier. So this suggests that improving the resolution has an impact on the SAO winds, but as you can see from the plot, it is not actually enough to increase the whole resolution from 85 levels to 242 levels, and it's not worth to have that kind of change just to see this small amount of wind magnitude change. So we will need to look at the next thing, which is the QBO nudging. So what I have done here is that on the left hand side, I have the control run, which doesn't have any nudging in it. And on the right hand side is the nudge run. So what we did here is we have relaxed the winds from almost 100 hectopascal to 10 hectopascal to the observed winds. So we have used ERA-5 here. And so the winds in this region is relaxed to the observed QBO winds there. And so we hope that this will kind of help to have the correct filtering of waves happening in this region, and hope to see what changes that will bring to the semi-annual oscillation. So as you can see here, there is a very small improvement in the westerly phase happening in the fact that it is a bit more longer now. But if we look at the easterly phase, we can clearly see a reduction in magnitude in the second half. So that suggests that there is a better annual cycle going on in the nudge trend. So I wanted to see why that is happening. Nudging in the QBO region kind of helps to, the suggests that nudging the QBO region helps to improve the SAO annual variability, and we will focus on why that is happening. Okay, the plot here is again the first Fourier transform in time of the zonal wind, and you can see on the not just the wind, and so that this is in per year, the x-axis. So the plot, this variability here is from the semi-annual oscillation, and we have the 1 year variability here, which is the annual variability, and about 2 years is the quasi-biennial oscillation variability going on in the control and nudge trend. Now the difference between control and nudge, if we look at the annual variability, it seems to be coming down, and in the QBO region there seems to be a pretty good magnitude in the annual variability, which was not there in the control trend. So this suggests that imposing the observed winds into the QBO region helps to have an annual variation of QBO introduced, and that somehow helps to have an annual variability in the semi-annual oscillation region too. So what do I mean by the QBO annual cycle? So if you look at this Pasqua et al. 2005 paper, he has plotted the QBO phase transitioning months histogram here, and we have easterly to westerly transition and westerly to easterly transition at 20 hectopascal and 44 hectopascal. And if we look at the 20 hectopascal, you can see both this transition is kind of focused on December, and this one is also kind of more concentrated on November and December, but it has a more distribution over the years. But we can see that there is a preference in month happening for the transition of QBO one phase to another. And if we move on to 44 hectopascal, this phase will be propagating downward, and it will reach around take around 4 to 5 months to reach the 44 hectopascal. And as you can see, there is a preference to those April, May, June months in the 44 hectopascal region, and which is true in the westerly to easterly transition too. Another thing here is the stalling that can occur due to Brewer-Dobson circulation. So whenever the BDC is kind of weaker, which will help to give the transition, which those months will have a transition from westerly to easterly, and that's why we are seeing this May, June, July preference at 44 hectopascal. So this suggests that QBO has an annual variability going on within it. And if we look at our control and nudge run, we can see this happening here too. In the nudge run, which is basically much similar to the observed QBO, we can see that December or November month preference in the transition, and control doesn't have that. It is kind of spread over the months, both in 20 hectopascal and 40 hectopascal. At 40 hectopascal, nudged runs have a preference of May, June, July, and control is all over the place kind of thing. So this suggests that like the annual in the control run, without this nudging, the model kind of fails to introduce this annual variability of QBO in it, and this is somehow affecting the semi-annual oscillation annual variability too. So I tried to look at different forcing terms and try to see where this issue is coming from. And so much similar to earlier, I have the meridional advection, vertical advection, resolved wave forcing, and gravity wave forcing, both for the nudge and control, and the difference is shown here. And so this is one reason why I haven't used unified model for our analysis earlier. Since unified model is based on a height coordinate system, it kind of has an issue in using our log pressure transformed Eulerian mean momentum equation, and it has this additional terming coming in, which we don't know what this unknown forcing is. So the issue here is the difference between nudged and controlled mostly comes from this unknown forcing term. So I can't actually assign into any particular forcing where the difference in the like the nudged and control is coming from. So what I know for sure is that the nudging in the QBO region helps to create an annual variability in the semi-annual oscillation, but we are not sure which forcing term is actually getting improved because of this. So, okay, so I have shown the model biases, compared the model and reanalysis, and showed some experiment, which we hope to see if there is any improvement in the SAO representation. And what we have from our analysis is that both underrepresentation of resolved waves and parameterized gravity waves kind of lead to the easterly bias that we see in the semi-annual oscillation. And we have explored different experiments in which, so the one in which gravity wave tracks were modified, it didn't show much improvement in the SAO, but the resolution experiments had some improvement, but it is not actually enough to increase the whole resolution from 85 levels to 242 levels. And nudging the lower level winds actually help to improve the annual cycle. So it suggests that if we have a better quasi-biennial oscillation in the model, that will help to have a better semi-annual oscillation also. Okay. Thank you.
Thanks, Aleena. We'll start if there are any questions in the room.
I have a couple.
Yeah.
Hi, Aleena. Nice talk.
Hi.
So the gravity wave parameterization, is that the gravity waves dependent on topography and convection, or just one or the other?
Convection actually. So in MERRA2 and vacuum, and unified model, it is a convection dependent. So wherever there is a precipitation maximum, there will be like more gravity waves happening in those regions. So yeah.
I wonder.
So it is the non-orographic gravity wave drag that mainly supports the semi-annual oscillation, not the orographic.
I see. So then I wonder if it's something. I wonder if the lack of improvement due to that is something because there's a fundamental problem with their convection or rainfall that you can't,
Yeah.
so maybe the gravity wave parameterization is okay, but if they have the bad inputs or the bad rainfall or bad convection, then it wouldn't be improved upon trying to change the gravity wave parameterization.
Yeah.
I wonder if that's a possibility.
Yeah, that is a possibility, but in the unified model, I have this another option where it doesn't actually depends on convection, but I can like give it as a uniform thing, and so I can change the magnitude of it and see if that will help to improve semi-annual oscillation in any case. But actually, that also didn't seem to help. But yeah, like in the convection based gravity wave drag parameterization, it is definitely like dependence on the precipitation will affect the gravity wave drag, and not getting the precipitation correct will indirectly affect this too. Yeah.
I see. Thanks.
Thank you.
Do we have an run?
Hi, Aleena. This was really interesting. This is kind of a blue sky question. In the stratosphere, you have these two different reversing wind systems, the QBO and the SAO. One of them is the period is really, it seems like phase locked to the annual cycle. And since it's on the equator, semi-annual is what you would expect. But the QBO, the period is really not strongly locked to the annual cycle, and the period actually seems to be related to the amplitude of the wave driving. So is there a reason why these two phenomena respond differently to wave driving in terms of their period?
So what happens in the semi-annual oscillation region is that there is this Brewer-Dobson circulation, a branch of Brewer-Dobson circulation going on there. So that gives an additional forcing, which kind of give rise to the annual variability, not annual variability, but the semi-annual variability of the semi-annual oscillation. But this is not present in the QBO. So QBO is mostly wave driven, but this, Brewer-Dobson circulation actually helps to give that semi-annual variability to the SAO.
I guess what I'm wondering is like why this doesn't happen in the QBO. Like why is the Brewer-Dobson circulation not able to impose a shorter period in the way that it does for the SAO?
So the meridional branch of Brewer-Dobson circulation happens at these higher altitudes, not at the QBO altitudes. So I think it depends on where the planetary waves break in the higher latitudes. So depends on that the Brewer-Dobson circulation will be modified, and so this meridional branch is happening at the altitudes of the SAO, I think.
Okay, thank you.
Hi, Ron. I have an answer for you.
Okay, well, we'll trade email. Thank you.
Hi, Ron. I have an answer for you.
I believe you. I mean, are there any other questions for the speaker?
Yeah, how about we see if there's other questions first, and then we can maybe continue this exact discussion.
Yeah.
So, in lower stratosphere, we have the tropical pipe. So
Tihan, could we just wait and see if other people have questions for the speaker? Is there anything else you want to?
Oh, sorry.
Yeah, thank you.
Yeah, no, it's good that we can check. There is one question in the chat, but I actually think it is from Tihan.
Yeah.
So, if you guys want to chat about this, and then Tihan, you can ask your question to Aleena.
Well, Tihan, why don't you ask your question to Aleena first, and then you and I could chat afterward.
So, do you be answer the question?
No, would you? I thought you had a question for Aleena. Did you want
to? Oh, this is at the beginning. So I found it's puzzling. Why do you show the ERA-5 data? Because ERA-5 data only for pressure level, they only show only released to public above or below 1 millibar, and above 1 millibar they don't show to public. Why do you show this flawed data? Why do you use the flawed data to this study? I don't understand you.
No, I don't use that data actually. That's why I eliminated that data at first. I used the MERRA2 for all of my analysis. I just showed that it has that flow there so that we can eliminate that data.
I don't think you should use that data. You give a bad reputation for ERA-5 data. They don't want to show this data. You should not show that data above 1 millibar level.
I have a question for Aleena. So earlier in the talk, you were talking about the three model biases that are apparent: the weaker westerly winds, the timing of when the westerly to easterly transitions, and then the weaker annual cycle. When you are looking at these biases, do you have an idea of which bias is most influential towards, a better representation of the SAO's interaction from a climate perspective? Like if you had to focus on one of these biases to correct, which one would you focus on?
So the westerly to easterly phase transition timing is kind of the most important one because it can actually affect the sudden stratospheric warming timings. And this phase transition timing will actually depend on the SAO westerly magnitudes because a weaker westerlies actually help to give this easterly transitions early on. So yeah, both of those things are kind of connected together, and getting that correct will be the priority.
Yeah, thanks.
Thank you.
Hey, Ron, you asked a question, so I want to answer your question. That question. So,
okay.
So you said why SAO have 5.5 years. My understanding is that in the lower stratosphere, middle stratosphere, we have tropical pipe, so that extratropical planet wave cannot propagate into deep tropics. While in the upper stratosphere, the planet wave can freely propagate in the equatorial region. This is why the extratropical can exert control over the upper tropical region. I cannot exert too much on the lower stratosphere region, I think.
Okay. All right. Thanks.
Okay.
Also, so you mentioned all these things. I remember the vacuum model have strong westerly bias of QBO. This westerly bias is detrimental for your simulating of SAO. You show the wave, the Kelvin wave, and Rossby wave, you show the figure. At the 10 millibar, you see clearly the vacuum model filtered too much of westerly wave, Kelvin wave, and while it do not feel too much westward wave. You see the picture. Do you remember the picture? Mirror and vacuum.
Okay.
Yeah, this
Here,
you see. Yeah, 10
Yeah.
millibar. Yeah, 10 millibar hectopascal because the QBO is strong biased in vacuum, so that the westerly wave already filled too much. I think this is play important role in the bias of SAO. So this is important source of error in simulating SAO.
Yeah, that is actually true. Like QBO can be absorbing most of the high westerly waves, and which will lead to lesser waves like available in the SAO region. And this can be one reason why the QBO nudging helped to improve the SAO representation. So more accurate waves are propagating upward, and not all are absorbed in the QBO region. So
yeah, this is why nudging is better. Yeah.
Yeah.
Thank you.
Aleena, have you I know it's a lot of analysis, but have you looked at how other models compare to MERRA2 other than just Wacom, and if like choosing a model that has a better QBO representation, if that further supports your point that a better QBO simulates a better SAO as well?
I have just looked at other models, but I have never looked at what their QBO representation was. So actually, yeah, that will help to see if this point is valid. Yeah, and yeah, have a look at that. Yeah. Thank you.
Okay, I don't think we have any more questions online. So if we don't have any more in the room, I think we can just give another round of applause for Aleena. This was really good presentation. And yeah, I think we can just kind of close out here. So thank you so much for signing on, Aleena. I know it's much later in the day there. But we really enjoyed this. Thank you.
Thank you. Thank you for hosting me. Yeah, that's okay.
Bye.
Bye.